Have you ever wondered what powers the sun and the stars? Or how we might be able to harness that same power here on Earth? Well, the secret lies in a process called nuclear fusion. At its core, nuclear fusion is a simple concept. It's the process where two light atomic nuclei combine to form a heavier nucleus. And in this process, an enormous amount of energy is released. This is the same process that fuels the sun and the stars, allowing them to radiate light and heat across the vast expanse of space. So, in a sense, nuclear fusion is like the powerhouse of the universe. But what if we could replicate this process here on Earth? Imagine the possibilities. We could tap into a virtually limitless source of clean energy. In essence, nuclear fusion is the powerhouse of the universe. Now you might ask, why should we care about nuclear fusion? Well, let's dive into that. Nuclear fusion is more than just a fascinating scientific phenomenon. It's a potential game changer for our energy future. This is because of three significant benefits that come with harnessing the power of nuclear fusion: abundance of fuel, minimal environmental impact, and inherent safety. Let's start with the first one, the abundance of fuel. Nuclear fusion primarily uses hydrogen isotopes as fuel. Now, hydrogen is the most abundant element in the universe. You can find it in water, which covers about 70% of our planet. And let's not forget, it's also present in the atmosphere. This means we have more than enough fuel to power fusion reactors for millions of years. Next up, let's talk about the environment. Unlike fossil fuels, nuclear fusion doesn't produce greenhouse gases. It's as clean as energy production can get. The only byproduct of a fusion reaction is helium, an inert and harmless gas. This means that fusion energy has the potential to power our world without contributing to climate change. And finally, there's the safety aspect. Unlike in nuclear fission, where a reaction can run out of control, fusion reactions are inherently safe. If anything goes wrong, the reaction simply stops. There's no risk of a nuclear meltdown or the creation of long-lived radioactive waste. So nuclear fusion offers us the tantalizing prospect of abundant, clean, and safe energy. But of course, this doesn't mean it's without challenges. In the upcoming scenes, we'll delve deeper into the mechanics of nuclear fusion, its challenges, and real-world applications. So buckle up and stay tuned as we continue our journey into the heart of the sun, right here on Earth. Now that we understand why nuclear fusion is important, let's explore how it actually works. Imagine heating hydrogen atoms to temperatures hotter than the core of the sun. This extreme heat creates a state of matter called plasma, where electrons are separated from the nuclei. This plasma is so hot it has to be contained in a special way to prevent it from touching and damaging the walls of the reactor. This is where the tokamak comes into play. Picture a donut, but instead of dough and frosting, it's made of powerful magnetic fields. This donut-shaped device is designed to keep the super hot plasma stable and contained. It's like having a sun on Earth, but it's kept in check by the magnetic fields of the tokamak. Inside this magnetic donut, something extraordinary happens. The hydrogen atoms in the plasma, under immense pressure and temperature, overcome their natural repulsion for each other. They collide and fuse together, forming a heavier atom, usually helium. This fusion process releases a massive amount of energy, far more than you would get from a similar mass of coal or oil. This energy is what we're after. It can be harnessed to heat water, produce steam, and turn turbines, resulting in the generation of electricity. But the fusion process doesn't just stop at one reaction. Each fusion generates neutrons which, despite being unable to be contained by the magnetic fields, can be slowed down by a blanket layer surrounding the reactor. As these neutrons are slowed, they transfer their energy into this blanket, keeping the fusion reaction going and creating a self-sustaining cycle of energy production. This entire process, from heating hydrogen to creating a self-sustaining fusion reaction, is what we mean when we talk about the mechanics of nuclear fusion. It's a complex dance of physics and engineering, all working together to harness the same power that lights up the stars. That's how nuclear fusion works, at least in theory. But what about in practice? As promising as nuclear fusion is, it's not without its challenges. Nuclear fusion requires conditions of extreme heat and pressure, akin to the core of a star. To replicate these conditions here on Earth, we need to heat plasma to a temperature of over 100 million degrees Celsius. That's several times hotter than the center of the sun. This creates a bit of a dilemma. How do we contain something that hot without it melting everything in sight? Enter magnetic confinement, a technique used to keep the superhot plasma away from the walls of the reactor. But here's the catch. Maintaining the stability of this plasma is like trying to hold jelly in your hands. It constantly wants to squirm and wriggle away. Moreover, to achieve a net energy gain, the fusion reaction must be sustained for a significant duration. Currently, most experimental reactors can only maintain the reaction for a few seconds or minutes at a time. For fusion to be practical, these reactions need to be continuous or at least last for much longer periods. And let's not forget about the fuel. While hydrogen is abundant, the specific isotopes needed for fusion, deuterium and tritium, are a bit trickier to come by. Deuterium is plentiful in seawater, but tritium is rare and needs to be manufactured, adding another layer of complexity to the process. Then there's the issue of neutron radiation. Fusion reactions produce high-energy neutrons, which can damage the reactor structure over time and also make it radioactive. So, adequate shielding and materials that can endure the bombardment of neutrons are critical. All these factors make nuclear fusion a highly complex scientific and engineering challenge. But don't let that dampen your spirits. The payoff of unlocking a virtually limitless, clean source of energy is too great to ignore. Despite these challenges, scientists and engineers are working tirelessly to make nuclear fusion a reality. Indeed, nuclear fusion isn't just a theoretical concept. It's being pursued by real-world projects, like ITER. The International Thermonuclear Experimental Reactor, or ITER, is a large-scale scientific collaboration between 35 nations. It's an ambitious project aiming to prove the viability of fusion as a large-scale, carbon-free source of energy. The project is currently under construction in southern France, and once completed, it will be the world's largest magnetic confinement plasma physics experiment. The goal of ITER is to produce 10 times the amount of energy it uses, a feat no fusion experiment has ever achieved. By doing so, it will pave the way for fusion power plants that could provide clean, limitless energy for our growing world. So, nuclear fusion, while complex and challenging, holds the potential to revolutionize our energy systems and help us build a more sustainable future.